If you write infrastructure as code like a simple top-down bash script, your enterprise deployments will eventually break. A procedural approach tells a system how to do something, step by step, which quickly becomes brittle at scale. Terraform operates differently. It is a declarative infrastructure orchestration engine. You define the final outcome, and it figures out the steps to get there. To understand how it actually works, we have to look at its operational model, which relies on 3 pillars. It is declarative-first, state-aware, and production-always. Moving from a single local file to a zero-trust enterprise pipeline requires navigating 8 core architectural domains. Mastering these domains provides the architectural framework necessary to engineer resilient platforms at scale. The engine functions by calculating the exact mathematical delta between human intent and cloud reality, then applying only the necessary changes to synchronize them. The entire process begins with HashiCorp Configuration Language, or HCL. This is the interface where you declare your exact infrastructure requirements. Because it requires strict type constraints and utilizes dynamic blocks for nested configurations, HCL forces you to catch structural errors locally before a single API call is ever made. This diagram shows how your HCL files feed directly into Terraform Core. Core is the central engine that parses your configuration files and maps out a complete mathematical dependency graph of every component. But the Core engine itself has no ability to speak to Amazon Web Services, Google Cloud, or any external system. It hits a barrier. To bridge that gap, Terraform uses providers. These are dedicated translator modules that slot in between Core and the target platform, establishing the secure connection necessary to push create, read, update, and delete operations. Once Core calculates the dependency graph, it hands the specific instructions to the provider. The provider handles the authentication logic and translates the graph into the exact API calls required by the cloud vendor. By isolating the calculation engine from the API execution layer, Terraform remains completely platform agnostic while still allowing you to orchestrate highly specific, vendor-unique resources. Within your configuration, the active execution units are called resources. A resource block is the atomic building block that explicitly commands Terraform to create a piece of infrastructure, like an EC2 instance or a virtual network. Conversely, when you need to reference existing infrastructure without altering it, you use data sources. These run safe, read-only queries against your environment, pulling in required IDs or IP addresses without risking modifications. As environments grow, engineers often duplicate these resource blocks across dozens of files. Copying and pasting infrastructure code directly guarantees severe configuration drift and maintenance bottlenecks. To solve this, Terraform uses modules. As we can see here, individual resource components are packaged together into a single, version-controlled container. By publishing these standardized modules to a private registry, they can be securely scaled out across massive engineering teams, enforcing strict don't-repeat-yourself principles. Standardized modules establish a repeatable library of infrastructure patterns that can be enforced across the entire organization. Declarative intent and API execution only function if the system has a persistent record of every resource it has previously deployed. That memory is the state file. The .tf state file acts as the absolute source of truth for your environment. This 3-way split visualizes the core mechanism of the Terraform plan command. On the left is your desired configuration. On the right is the real-world cloud API, and in the center is the state file, mapping the two together. When you run a plan, Terraform compares these 3 distinct data points to calculate the exact mathematical delta, generating the precise execution path needed to make reality match your code. Storing this state file locally on a single laptop works for one person, but in a team environment, concurrent executions will overwrite each other, causing instant corruption. Production environments migrate this file to remote state backends, securing it in centralized storage like AWS S3 or HashiCorp Cloud. Storing the state remotely also allows you to enable state locking. Using a database table like DynamoDB ensures that while one engineer is applying changes, all other write access is locked out, preventing catastrophic data loss. To manage multiple identical environments like dev, staging, and prod, Terraform utilizes workspaces. This isolates multiple state files within the same backend, ensuring a change in staging never accidentally targets production. The critical realization here is that Terraform does not actually manage cloud resources. It manages state.
If the state file is lost, corrupted, or ignored, the entire deployment pipeline fails. Moving these mechanics into a live production environment requires a highly structured operational workflow, complete with strict security gates. Configuration begins with a layered security model for input variables. Values are evaluated through strict precedence rules, starting with baseline defaults and overriding them through specific variable files or command line inputs. Because state files often contain sensitive information, hard-coding passwords or tokens is a massive vulnerability. Enterprise setups integrate external secrets managers like HashiCorp Vault and utilize dynamic provider credentials to inject temporary rotating access keys at runtime. This flowchart tracks a secure continuous integration and deployment pipeline. A developer commits code, and that Git push automatically triggers a Terraform plan on the server. Crucially, this plan is output to a specific locked file, .tf plan. Saving the plan guarantees deterministic execution, ensuring the exact delta evaluated in the testing phase is the only thing executed in production. Before that plan is applied, it must pass through an automated policy as code security gate, using tools like Sentinel or Open Policy Agent. If the plan violates compliance rules, like deploying an unencrypted database, it is blocked immediately. In a mature organization, human engineers never run Terraform Apply directly from their terminals. The automated CI/CD pipeline and the policy rules enforce an absolute boundary between human intent and physical execution. Even with a secure pipeline, engineers inevitably face the need to refactor their configurations, like renaming a critical module. By default, Terraform sees a name change as an instruction to destroy the old resource and build a completely new one, which is catastrophic for a live production database. You can override this destructive default behavior by applying strict lifecycle meta-arguments, such as create before destroy, which forces the system to provision the replacement before tearing down the original. For logical refactoring, you can inject moved blocks into your HCL. This explicitly tells the dependency graph that a resource has simply changed its address, avoiding replacement entirely. When manual intervention is required, the Terraform state move command allows administrators to safely restructure the contents of the .tf state file directly, completely bypassing the cloud APIs. Beyond state manipulation, the Terraform plugin framework allows teams to develop custom providers in Go, bringing internal proprietary APIs into the same orchestration logic. HashiCorp further extends this ecosystem with the Cloud Development Kit for Terraform, or CDKTF. CDKTF allows developers to write infrastructure using familiar imperative programming languages, like TypeScript or Python. The toolkit then synthesizes that imperative logic down into the standard declarative HCL graph. The platform orchestrates any system with a programmatic API, provided the underlying state graph remains correctly managed. This topology map illustrates the complete architecture in motion. Raw HCL syntax defines the intent. Core calculates the graph. The state file locks in the truth. Policy gates verify the security, and the providers execute the commands against the external infrastructure APIs. Terraform is a rigorous orchestration engine, driven entirely by the continuous mathematical reconciliation of state. Whether deploying a single server or a global platform via CDKTF, this architecture provides the foundation for reliable, scalable infrastructure automation.